Hello, I'm Philip Stoughton. I'm on the Scoop Studio at Prod17 2017. I'm joined by Karthik from Indium. Karthik, thanks for stopping by to chat. Just wanted to get an update on what's new with Indium. You've always got some new things at a show like Prod17. What have you bought for us this year?
Morning, Phil. I'll talk about the automotive umbrella, where it's a fascinating space to be in at this point in time. So broadly speaking, before I get into products, I'll talk about the drivers that have challenged us to come up with some of our new technologies and products. So the key drivers in automotive we see are more electrification, more hybridization, the mild hybrids, and then leading to the different levels of autonomous vehicles. And because of these drivers, the challenges that are posed on materials would now include, enhanced electrical reliability, ultra low voiding, alloy reliability in terms of the ability to withstand more thermal cycles. As an example, from minus 40 plus 125, which was rated for 1,000 cycles, that needs to now withstand 3,000 to 6,000 cycles. And the service temperatures increasing from 125 degrees C to 150 degrees C and beyond. So you got the drivers, you've got the challenges, and now we're going to talk about the products that address these challenges. So when we talk about electrical reliability, it's a big deal, because when you talk about more electrification, it's more power, more voltage. And when you talk about no clean flux residues, what's going to happen to the residue when you're now going to jack up the voltage from 10 volts to 50 volts? And you're not talking about 168 hours, you're talking about 1,000 hours. You're not talking about an SIR threshold of 100 megohms, but you're now talking about a minimum of 5,000 megohms. So, all the rules have changed. So how do you engineer your flux chemistry to still be able to withstand, this electrical reliability? By the same token, voiding. With more electrification comes more power, and therefore you don't want hot spots. You got to get the heat taken away from the power source. And therein lies, how do you engineer the flux chemistry to go with lower voids? And that means engineering the flux to make sure that you reduce your overall void content, but also making sure that you don't have a big lake void in the center. That's where the power dies. So breaking it up into smaller voids and moving it away from the center. The third one is alloy reliability. This again is a huge area we are working on, because, like I said, the current assemblies were rated to 125 degrees C service temperatures. But when you're now talking 150 and beyond, given your substrates, components, the CT mismatches involved, there's a lot more chances for failures. And nobody wants to be the party responsible for somebody having an accident with these advanced vehicles. And that's where alloy reliability comes in. So if you look at traditional SAC solders, as your operational temperature increases, the delta between your service temperature and the melt point starts dropping. Now this becomes a problem, because the SAC alloys fatigue resistance goes down. What I mean by that is, when you do cold hot thermal cycling, the alloy is not able to withstand this. So the traditional approach was to make the alloy a lot harder. But when you talk about your higher service temperatures, you also need a certain degree of ductility for the alloy to absorb the stress rather than transmit it to the component of the board and that breaking off. And that's where, again, alloy technology becomes key, because the approach was just make it a lot harder without building the right degree of ductility, especially for service temperatures of 150 and beyond. So that's where we've got our Indalloy 276 that gives it that right balance. So I've been talking about PCBA. Again, in the automotive umbrella, we got power modules where it's the same drivers, more electrification, higher electrical reliability, and more Rs. And when you look at power modules, IGBT power modules, you got your die DBC base plate stack up, and DBC to base plate, your bond line controls got to be uniform. And over the last 3 years, what we've been seeing is, to maintain bond line control, wire bonds are stitched and trimmed, and this increases the cost of ownership. So we've got the informs, which are preforms with an embedded metal mesh, so which is a total drop-in with a preform, and gives you the lowest cost of ownership and increases reliability by a factor of 2 to 3x.
Okay, so You got it all in one answer, everything that's going on. Last question, you mentioned ultra-low voiding in both of those. You've had this Avoid the Void campaign, but that's been much more than a campaign. There's a whole engineering program behind that. How's that gone, and how significant is that in both the automotive and other industries?
I would say Avoid the Void has been, just the fact that you use it's rolling off your tongue. It's been a very successful campaign. But I think from a fundamental technology level, it's put the spotlight on voiding as it should be, but it's also helped create the right reasons for attacking voiding, as well as dispelling some myths about what the danger of a void is. For instance, if you're talking about having voiding under 10% across all components in a board, it begs the question, why? What does a void under 10% for an 0805 package going to do? That doesn't mean it's okay to have a large degree of voiding. It just means we got to delineate the thermals versus the mechanical reliability and address it on a case-by-case basis.
Yeah, and that's the important thing. And what's great to see is there's so much debate in the industry that campaign has brought up, and you've got the oven manufacturers involved, you've got people like Kick and the people that are involved in thermal profiling software involved, so it's been great. Karthik, thanks for your time, thanks for stopping by.